Hey guys, it's Coach Sharf. Welcome back to my Algebra 2 notes and examples videos. Today we are going to do a couple of examples on graphing polynomials. We're going to put the graphs into the Desmos graphing calculator, and we're going to work on identifying all the characteristics that we can by looking at the graph. And, if you're watching this currently, maybe even in the future, if I use the same worksheet, so if you're watching this in February of 2021, the first two examples are going to be number 1 and number 6 on your worksheet. So you already have 2 problems done, then just got to do those 6 on your own. All right. Let me share my screen, go to Google. So actually, I guess the first thing I need to share is, let me back that up. Again, if you're watching this in I don't want to say real time, but when I'm originally posting this is the worksheet that you have. It's in Canvas, in your assignment in Canvas. So you got all these different polynomials, and we have all these different characteristics, domain range, your x and y intercepts, turning points, if it's an even function, odd function, or neither, intervals of increase and decrease in your end behavior. So we got to identify all those. So we got to type each function into Desmos and be able to identify them. So now let's go back to Google. So if you're on your laptop and doing this, you can go to desmos.com/calculator and it'll take you right to it. Okay. If you go to desmos.com, it'll take you to the main website, which I'm also going to get to in a second. But even if you just type in Desmos and hit enter, this should be the first thing that pops up. Again, this will take you to the main website. This will take you straight to the graphing calculator. If you happen to click on this, graph calculator's right up here. It's also under math tools. I'm going to show the math tools for a reason. If y'all see the symbol by that. So again, you can actually download Desmos onto your phone. It's an app, right? Same symbol right there. If y'all can see it in the screen in the corner, okay? So you can download it on your phone as well. But let's get into the graphing calculator. And, again, I can't really show you a keyboard. So if you know how to type in exponents on your keyboard, it's that if you look above 6, there's that same little caret that you have, wrong way, on your calculator. So you would type in X, hold the shift button, hit 6, which would, that's what I'm doing right now. I just have to, so hold the shift button, hit 6. That's what throws it up there to be an exponent. All right. You can also hit this A to the B button, A to the B power button, which throws it up there as well. So our first equation started with x cubed, then it was minus 5x. You can do the same thing to get x squared, shift 6, which throws it up there. You can hit the A to the B button, but with the square, you can actually just go ahead and hit a squared and automatically throw it up there. Minus 4x plus 20. All right. So as y'all can see, if I can move my head out of the way, we can see where our graph crosses the x-axis, but we can't see the entirety of the graph. Okay, so depending on what you get, you might have to zoom out a little bit. All right, so now we've zoomed out, we can see the whole graph. You got a couple that are kind of close here, but if you kind of look at, there's all these gray points, which are going to be our significant. Sorry about that. I don't know if the screen cap got that or not, but those are our significant points we're going to look at. But what I'm going to do over here in the blank area, I'm going to write all of our characteristics that we're looking for. I'm going to try to alternate colors to make it a little easier for y'all to see. So we had domain, range is next, your x-intercepts, your y-intercepts, your turning points, if it's even, odd, or neither, your increasing intervals, intervals of increase, decreasing intervals, intervals of decrease, and your end behavior. All right, so we'll do those in green. I feel like blue was kind of close when I did it the other day. I don't even know what I could do that would be different though. Maybe this is orange. So your domain, your range. That's close enough. It's kind of like Miami colors too. X-intercept, Y-intercept, turning points, even, odd, or neither. Intervals of increase, intervals of decrease, and your end behavior. All right, so the reason why I was pointing out those points is because, that's the most identifiable thing. We can click on them and it'll tell us what those points are. Now we just got to figure out, in terms of x-intercepts, y-intercepts, and turning points, what they are. So we're going to start with these. They're on the x-axis. Obviously, there are x-intercepts. So for our x-intercepts, we have -2, 0, +2, 0, and +5, 0. So the thing to remember about our x-intercepts is that, again, our x-intercepts are the same as our roots, our solutions. Adjust the camera a little bit. Our roots, solutions, when we are trying to solve the polynomial. Again, when we solve this in the packet, we got that the roots were -2, +2, and 5. And then, of course, they're all rational and real. So there are roots. There also are y-intercepts, or x-intercepts, excuse me. Going back to our y-intercept now, 0, 20, where it crosses the y-axis. Again, it's pretty close. If you need to kind of zoom in there to verify, yeah, we could see, okay, that's where it crosses the y-axis. You should know it's where it crosses the y-axis because my x coordinate is 0. I haven't gone, left or right. I'm on the y-axis. So that's my y-intercept. So let me change to orange. So my y-intercept is going to be 0, 20. And again, guys, with our y-intercept, it's whatever this constant is. Because if I plug in, it goes back to slope-intercept form that this is my y-intercept, okay? Since x is 0, if I plug in 0, 0 cubed cancels out. 0 squared is 0 times -5 is 0. -4 times 0 is 0. So it just leaves me with that 20. So it's the same idea. All right. And just as FYI, I'm going to try to go a little quicker. Again, not to make this video too long. Okay. All right. So now we're back a little bit centered. So now we got our turning points. And we talked about the turning points in the notes video. Again, they're kind of like a vertex. Again, if we even zoom back into what we had, we can't see the other red line. So if you kind of had it by yourself, if you had this by itself and we said that, both of these sides kept going down -infinity forever, this looks like a vertex. Of course, when we zoom out, we see there's more to the graph than that, but, it's kind of the same idea as vertex. It's just that we don't call it that. So I have that one, and then I have this one down here. How turning points do kind of compare to a vertex is that we call them maximum or minimum values. However, with the vertex, if I actually had a parabola, the vertex is, obviously that's the lowest point. The green line didn't go down, and so we just call it a minimum. If it was flipped upside down, a maximum. So we have to introduce, I think adjectives is the right word. I'm not an English teacher. We have to introduce adjectives for those minimum and maximum points when we're talking about larger polynomials, okay? So for -0.361 and 20.745, this would be what we would call relative maximum. So I'll go ahead and write that down. So we'll say a relative maximum, okay? So -0.361, 20.745. We call it a relative maximum because, again, the best way to really describe it is it's the highest defined point. Okay. It's, depending on your definition, and I think if you look in the book, it says it's, it's the highest point of any other points that are around it. It's the highest point on a part of the graph that's not going to infinity. Obviously, these points are higher, okay? But this section of the graph is continuing to go to infinity. So we can't say any of these are a maximum value because the graph keeps going past all these points and it's going up to infinity. So it never gets to a last value that we could call a max value, okay? So that's a relative maximum. And then down here is going to be a relative minimum for the same reasons. Yes, these points are lower, but all these points are on a part of the graph and down to negative infinity. So we would say a relative minimum at 3.694, negative 12.597. So we use the ordered pairs, but the actual value is our y value. So that's the y value is the relative max and relative minimum value, but we list it as the ordered pair. I'm gonna give y'all a minute to get that because I need to erase what I just wrote to kind of free back up room on my graph. So make sure that y'all got that. Okay. Again, you can pause it real quick if you need to. All right, I'm gonna go ahead and erase. All right, so we've identified all 6 of those points. Now we can kind of start running down everything else. Domain, with the same as quadratics, everything we're doing right now, our domain is gonna be negative infinity, positive infinity. Again, a couple ways to think about that. If we're looking at the graph, this end is mostly going down, but it's going slightly to the left as well. Again, you can zoom out on this as far as you want just to make sure that the graph, at some point, way over here doesn't turn and come back up. It doesn't, I promise. So nothing's going to stop this from going down and to the left forever, but the left's the key part for our domain. And then this is mostly going up slightly to the right. Nothing's going to stop it from doing that. So it's going to keep going left to negative infinity x, right to positive infinity x. Our range, again, a little different from how we've had it with the parabolas. With the parabolas, I clearly had a lowest y value or a highest y value. But if I look now, again, even kind of what I just said, this end is going down and slightly to the right, but there's nothing that's going to stop this from going down to negative infinity y. Nothing that's going to stop it from going up to positive infinity y. So my range would also be negative infinity to positive infinity. All right, jumping down to even, odd, or neither. So again, we talked about this, even or odd functions in the notes video, so you can go back and watch it if you need a refresher. If we're looking at our function, you're looking for variables with only even exponents and a constant, or variables with only odd exponents. If you see at least one even exponent, I don't know in reverse order, but one even exponent, one odd exponent, you automatically know it's neither. If you're looking at the graph, it's either going to have that even symmetry, so it's going to look like it reflects over the y-axis, which this clearly does not, because ignoring this hump since it's kind of right on it, but with this one you would have a hump here, and then since this line goes up, you'd have a line coming up there as well. If it has that odd symmetry, it has to go through the origin. And again, it would kind of be that 180-degree rotation to where if you had it on your paper, had your screen, you flipped it upside down, it looked exactly the same. But, this doesn't go through the origin, so I automatically know it's not going to have that odd symmetry. So this is going to be neither. And if you're doing the worksheet, the one drawback for me pulling all those problems out of the packet is all the problems on from the packet that are going to be on this worksheet are going to neither be even or odd. I had to add one problem, which is actually the problem I'm going to do next to show y'all the even symmetry. Okay, it'll have that even symmetry. All right, so your intervals of increase or decrease. So again, this is I think the most confusing thing if you don't understand it. we're talking about as our graph is going up, so the y values are increasing or going down, so they're decreasing. But we talk about our intervals of increase and decrease in terms of our domain. So over what values of x are my y values, is my graph increasing, and over what values of x is my graph, my y values decreasing. So you read it from left to right, and no matter where you start reading it from the left, when we hit this first line of the graph and we start tracing it to the right, it's clearly going up, okay? So it's increasing, and it would be increasing from negative infinity x, so we're still kind of staying on here. So it would be increasing from negative infinity x all the way to that turning point, which again was negative 0.361. So my first interval of increase, my y values are increasing from negative infinity x to negative 0.361x. My graph then turns down. You see the y values are falling here. It's decreasing, negative slope, until we get to that turning point. So it's over this little bit of our x values going along the x-axis. It's decreasing. So it's decreasing from negative 0.361x to 3.694x. And then it turns around and starts going up again. And again, this is where we could say it's going up and to the right forever. So it's going to continue to increase as my x values go right. I know it's very crooked. As my x values go right to positive infinity. So I have a second interval of increase. So I'm going to put this u, which represents a union. Again, y'all probably haven't seen it for a while because we didn't get the probability at the end of last year in geometry. That would have been the most recent place y'all would have seen it. So it's increasing from 3.694x to positive infinity. So again, we're trying to cover our entire domain. We got negative infinity to negative 0.361, negative 0.361 to 3.694, and then 3.694 to positive infinity. So we've covered our entire domain. All right, last thing is about our end behavior. And again, we could talk about our end behavior in simple terms, and it's pretty easy. The left end of this graph is going down to negative infinity y. The right end of this graph is going up forever to positive infinity y. But we have to talk about it with certain notation. So as this graph, again, it's mostly going down, but slightly going left. So we're saying as this graph is going left slowly to negative infinity x. So as my x values approach negative infinity, my graph is going down. So I'm going to say f of x because the graph represents our function. Our function values approach negative infinity y. Okay. Again, the thing I told y'all is that if you're more comfortable putting y here, more comfortable putting y approaches negative infinity, that's fine. But again, the thing to remember is on test situations, probably could say f of x. As long as you remember f of x and y are interchangeable, if you want to put y instead, that's fine. So as x approaches x values approach negative infinity, keeps going left towards negative infinity x. The value of my function, which again is defined by our y values. So as our x values approach negative infinity, our y values approach negative infinity. And then this side, again, slightly going right, but it's never going to stop going right towards positive infinity x. So for there, as x approaches positive infinity, I'm just going to leave it as infinity. I'm not going to put the plus sign. Our function values approach positive infinity y as well. So As f of x approaches positive, as x approaches positive infinity, f of x approaches positive infinity. So left end going to negative infinity, going down to negative infinity, right end going up to positive infinity, or right end going right to positive infinity, also goes up to positive infinity. All right, so there's our first example. And again, I'm not trying to make these videos too long, so I'm going to go ahead and cut this one here, and I'll do another video for the, oh, excuse me, sure. I'll do another video for the second example, and I'll get all these posted. So I'm going to try to record it at some point. Might not be. I'm recording this at the end of first period, because I'll let first period go work on this on their own. So it might not be till lunch till I get the other video done, but I'll have them all up, and y'all can use them to help you out. So till the next video, I'll see y'all then.